Imagine like a sheet kind of like waving around in the wind, you know, and you say stop, okay, and you look at that surface, you can find the highest and lowest points on a surface using something like this. You'll have an objective function and a constraint. Objective function, constraint. Next one. So I'm going to do the next example in here. This was that beer can problem. It's a 1 liter beer can. I'm going off my notes. I tell you that I want to make a beer can that's a right cylinder, right meaning 90 degrees. So I have a right cylinder. It must hold 1 liter, which is 1,000 cubic centimeters. Find dimensions. Dimensions of the can with smallest or I should say the least surface area. Why would anyone want to answer this question? Why would it be useful?
Surface area affects exchange.
Okay. Okay. So it could have something to do with energy transfer, heat transfer. Less material. Like let's say that I'm shipping out beers a can, right? There's a lot of different ways I can make a can to hold 1 liter. What I want is the one that I have to order the least amount of aluminum for, right? I mean, imagine a can that looked like a test tube, right? You know, that was maybe like 1 millimeter wide and very tall and held 1 liter. I would use a lot of aluminum to make that. Well, that's what the video was trying to get you to see, is that you can have a can hold 1 liter that has a certain surface area and then change the shape of the can, still hold 1 liter, but now you have a different surface area. Right? There's so many ways to hold 1 liter. Which shape can uses the least amount of surface? Because that's what we want to build, right? That's what we'd like. Okay. Yeah. All right, so let's try and set this up. Read and understand it. Draw pictures. I've kind of already got a picture here. If this is a can that I get to create, then it's going to have some radius and it's going to have some height, right? Yes? What is the variable we want to optimize? So I'm looking at, I'm doing step 3, introduce notation. Determine the variable to be optimized. Find the objective function. So surface area, right? You would say, I tried not to use the word minimum because I'm trying to kind of sneak it in here, but it's hard to sneak minimum in without being obvious. The smallest surface area means minimum surface area, right? So minimum or maximum in some way is going to be given to you in the problem, right? Somehow. That determines the variable we're trying to optimize. So I don't like writing SA, so I'm just going to put A to mean area. Is that okay? So I want to optimize A. So I'm trying to optimize A. Okay? So what do you need? Yeah, I mean, what's the area of a can? You need to be able to figure that out. What is the area of a can?
Cylinder volume equals IR squared H.
Yeah, Okay, look. Look at me real quick. I'll show you this.
Oh, okay, it's pi r squared h. No.
Look, everyone. Here's a can. Okay? What's the area of the top of the can? What's the area of the top of a can? It's the area of a circle, right? What's the area of a circle? Nope. Pi r squared. Pi r squared, right? That's a circle right there. So that's pi r squared on top. What's the area of the bottom? Pi r squared, right? Now, take your scissors and cut this can open. Okay? Just cut it open. What do you have? Length times width. How high is it? Well, the height of the can, isn't it? How long is it? It's the circumference of the circle, isn't it? Which is 2 pi r. So if you take that can and you cut it open, you have two circles, right? I've cut it open, taking the tops, the two circles, pi r squared here, pi r squared here. This is the height of the can, and the distance across here is the circumference of the can, which is 2 pi r. So the area, the surface area of a beer can is the area of this part, which is 2 pi r h plus pi r squared plus pi r squared, so 2 pi r squared. You don't need a formula sheet for that. It's easier to reference. But this is one of those things that I like to point out when I can, the difference between memorizing something and understanding it, right? If you can just visualize it, you can see where it comes from. So that's the formula, though, right? You have your formula sheet just in case, right? 2 pi RH plus 2 pi r squared. How many variables does A depend on right now? What would I need to know in order to tell you the area of this can? The radius and the height, correct? We cannot find the maximum and minimum of a function if it has two variables in it. We need a single variable. So the only way we can get this down to just r and just h is to use what? What did we use in the last problem? Because we drew a rectangle. We say, oh, we could draw any rectangle we want. What was it that made us be able to eliminate one of the variables? The constraint. That's right, the constraint. So what's our constraint in this problem? What is it about this beer can that has to be true? It's got to have good beer in it, right? Can't be skunky beer. Well, what is it about the can that has to be right? The volume. It has to hold 1 liter. Yes, question.
When you cut it, isn't the length just the circumference length?
That's this length, but I want the area. So length times height gives you that area right there.
Why do you have to have the r if it's just the length of the circumference times the height?
Why do I need the r? 2 pi r is the circumference of a circle. See, when I took that can, 2 pi r. So you're okay with it then? Okay.
2 pi r and r squared is different.
Yeah. We're good? Okay. All right, so we need the objective function, right? Or not objective, we're getting there. The constraint. This can't be just any beer can. It must be a beer can that holds 1 liter. So what does that mean? The volume must be 1 liter. Now I'm going to use 1,000 cubic centimeters instead of 1 liter. I'm doing that because then my radius and height answers, whatever it is, will be in centimeters. What is the volume of a can, though? What's the volume? It's a different formula. It's pi r squared h, isn't it? Pi. Are you looking sphere or something? Okay. Pi r squared h is 1,000. right? So isn't that an equation right there, a constraint? I know that pi r squared h must be 1,000. So can you solve that equation for either r or h? Which would you like? H? Yeah, me too, because then I don't have to do a square root, right? So let me, how do I get h by itself here? Divide both sides by pi r squared. All right. Now, are you ready with that constraint to come back to the objective equation and try and plug in, replace h? So a equals 2 pi r, but then h is 1,000 over pi r squared plus 2 pi r squared. Anything good happen there? I do get a pi to cancel here, and one of the r's, right? And so I have what, 2,000 over r plus 2 pi r squared. Questions? Is that now an equation that only the a only depends on one variable? So I can write it as a of r equals 2,000 over r plus 2 pi r squared. That's my objective. What should I look at next? Before the derivative, be careful. This is a critical step. I mean, you'll need the derivative no matter what, but yeah, is it open? Is it an open interval or a closed interval? So what's the variable? R. Is there a restriction on R? R is the radius of the can. Is there a smallest radius it can be? Can it be 0? Look at your function for area. Not only that, look at h. If you try and plug in 0, what's your height then? You can't make a can that has a 0 radius. You cannot make a can that has a 0 radius and hold 1 liter. Can't happen. Right? Well, but let's talk about the rectangle. There was nothing on the rectangle except for the fact that the total length of the sides had to be 100, right? So when I used 50 on each side, I still had all 100 feet used. It's just the other 2 sides had 0. So my rectangle didn't form a rectangle, but I still have an area. The area was 0. So I didn't have any true violation of any mathematical operation there. Does that make more sense? Here, if you try and let r be 0, your height is undefined and you won't be able to hold the liter. Now, is there a maximum radius? Think about this beer can. I mean, I could have this ridiculous beer can, right? That one right there. It's just like a wafer. It's just like this big wafer sitting on the table. You could I keep letting that radius get bigger? And what happens to the height? Gets smaller. But you could go forever, right? I could have a radius that's 3 miles long and the height would be infinitesimally small. So it's theoretically, there is no restriction on radius. Do you see that? So what